Hello and welcome back. In today's video, I'm going through setting up the charging circuit using the TP4056 and the surrounding protection circuit that's typically done with the TP4056 circuit. These parts are obviously very common, but it's good to know how to set one up in KiCad. So I'm just going to do it for this, and then we can use some batteries for this power board if we need to in the future. It's unlikely we'll be using a battery, but I'm just going to set it up, make it a bit more portable. So the first thing on this circuit, obviously we did the buck boost converter last time. If I go into the component symbols, we don't have TP4056 available, so I'll need to create one. So to create a part, you can basically go to the symbol editor and then file. I'm going to make a new library for this. I'm going to make it a global library so I can use it in the future. And then I'll go into documents, KiCad is fine, 8.0, then make a folder in there called my library. So now I have this library in there, and inside the library I'm going to make a new symbol. The symbol name is going to be TP4056, and I'll use the U designator as I don't have any issues with that. So then I'm going to press OK. So you basically get this interface here. So U is the designator that we selected. The next thing I'm going to do is place down all the pins. So we have obviously the VCC pin, which is pin number 4. Just to show you where I'm going this is from the datasheet of the part, so TP4056 datasheet. Unfortunately, a lot of these datasheets are going to be in Chinese. I am basically recreating this part over here. You got VCC on pin 4, you got CE on pin 8, you got the charge, you got the charge pin on pin 7. You can see the bar over the charge label. That means the pin is active low. So what I'm going to do is put the inverted graphic style on KiCad, and that will basically do the same for me. The next one you can see is standby, and again this is an inverted pin, and the pin number is 6. You can see I'm making mistakes already. This should have been pin number 7. And on the other side, we have the battery pin. That is an output, and that's pin number 5, and it is not inverted. Don't mind if this symbol is a little bit bigger than normal, as long as everything fits in properly. I'm just going to copy that and the program and the temperature pin here. If I go into this, I can basically edit this. So temp, and temp is pin 1, and battery, I'm going to change that to prog, and pin 2. So the last pin that I need to do is the ground pin, which you can see over here. So for that, I need the up version of the pin. So obviously that's the ground pin, and the pin number is 3. So after doing all of that, I'm going to put down a box, and what you should be able to do is make the box, I'm not sure what the standard KiCad color is, but it's somewhere around here. And the last thing, I'm going to add in TP4056. I've used the text box, gives me the ability to put down the text in the middle. It's just a bit easier to read. So just to double check this, we've got VCC on pin 4, chip enable on 8, the charge is pin 7, the standby is on 6, ground is on 3, and program is on 2, and the temp on 1. Finally, the battery pin is on pin number 5. What I'm going to do now is just save this, and basically I should be able to now import this part into my schematic. I do want to find the color because that looks horrendous. So let me see what that color is. So if I go into edit symbol and double click this box, fill with body background color. Okay, if that's available, I can do that. Otherwise, I can just copy these numbers. I'm going to go back into the footprint or the symbol editor. I'm going to open up the part in my library. So if I just do a search for it, TP4056, double click on this, background fill color 2194, 60, and 61. Save this. Now it doesn't look horrible. I've got my part here. for TP4056. The next part I need is DW01A. And again, that symbol is not available as well. So I'm going to create the symbol for that and all the other components that I need for this circuit. So now I have all my parts created. So I have my TP4056. I'm going to add in my DW01A. So just placing them randomly for now, and then I'll organize the circuit. So you can see I've got all three symbols that I've just created. They're slightly different colors, but I can sort that out later. The first thing I want to add is the terminals for the battery connections. I'll see if there's anything specifically available for that. If not, I will just add in some headers. So I've just selected some random connect. I think these connectors have strain relief built into the footprint. So I'll see what they look like when I start using them. So obviously our input voltage is coming from here, so which is going to be V bus. I'm just going to use this symbol here and put that onto the V bus side, and then take that, rotate it onto this side here. The first thing I'm going to do is connect up this pin, so that pin 5 directly goes to the output, and I'll try to find some LEDs. So the VCC will connect up to the 5 volts V bus, and then I've got some LEDs that I will be connecting to this point here. These resistors need to be 1K. So the first one I'm going to connect up is basically this one here, and then the second one, that one there. The chip enable pin I'm going to connect directly to VCC. So pin 2 in this case is used as a programming pin to program how fast the battery will charge or how much current will be pushed into the battery. Setting a resistor on this pin with a value of 10K will charge the battery with a current of approximately 130 milliamps. Setting a 1.2K resistor will fully use 1 amp. So I'm just going to set it to 1.2K for now, and then we'll see how well that works going forward. the battery management IC. I'm using a recommended connection. So for that, I also need these two MOSFETs. So the inside here, there's two MOSFETs that have been connected together internally. The symbols here basically, so that's gate of MOSFET 1, that's gate of MOSFET 2, and that's the source, and then you got D1, D2 here, which is the drain connected together, and you got G1, G2. So essentially, this is what it looks like. You can see the two drains are connected together. You've got the two gates, which are separate. I have mislabeled this pin over here, so that should be D1, D2. And then you got the two sources for the two MOSFETs separated as well. So you got S1 and S2 on this side. And this will connect to this battery management IC. So let me correct the component first, and then I will go to connect it up. Now, since I've corrected this part in the library, you can see this part over here is not corrected. If you press this button here, you can basically update the selector symbol from the library, and that brings in the latest model. So you can see now it's all good. So what I need to do here is basically connect S1, which is the source of the MOSFET 1, to pin 2 through a 1K resistor. So to do that, I'm just going to grab this, put a 1K resistor over here so that's out of the way, and then that will go to S2. Pin 3, I will need to connect to the gate of the same part. So that would be gate of 2, which is down here. The first MOSFET, which is the source of the first MOSFET, which is S1, I'm going to connect that to pins ground, and basically I'm going to add a decoupling capacitor to this circuit as well. So I'll just move this component to the side and add a decoupling capacitor somewhere around here, as neat as I can make it, because it's starting to look a little bit messy, but that's all right. So I've got my decoupling capacitor in place, connect up my ground, and I need to connect this to ground as well. The OD pin, I need to connect that to the gate of the first MOSFET. Now I can basically leave these two pins unconnected, and so that it doesn't flag any errors, I will just put a no connect flag on them. And the TD pin I can also leave unconnected. What I'm going to do here is move these two pins on this side and add some net labels on here. And I will do the same on this side here. So I've got my plus bat. The last thing is to connect the negative terminal of the battery, and I'm just going to change that symbol to minus bat and add that symbol over here. So that should be connected to these two pins here. So as far as I believe, this is the circuit that we need using the TP405. The reason I'm using this part is because it's very common, so I thought it might be useful for some people to see this. So you can see this circuit is a little bit different to what I was showing you when I did the schematic capture. Basically, what I've changed is the way this part looks. So I made this change just to make this circuit look a little bit neater. As you can see, it's not crossing all over the place now. And I've added a 0.4 ohm resistor here as recommended from the datasheet of the component from this section here. So essentially what I'm doing is this, copying this part from the datasheet, as you can see over here. And then I have added a DW01 and a dual MOSFET component FS8205A. So let's now talk about how this circuit works. TP4056 is a very commonly used lithium ion battery charger IC, and I guess its main job is to charge single cell lithium ion or lithium polymer batteries. And they work by providing a constant current which you can see on this chart on the data sheet. So on this axis, obviously you've got the battery voltage, and on this axis you've got the charge current. So obviously using the program pin, and by setting a 1.2 kilo ohm resistor down to ground, we can set the maximum charge current to 1 amp. Let's say you connect a dead battery and it's very low voltage. The TP4056 basically acts like a linear regulator and will limit the current internally to roughly about 100 milliamps until the battery voltage reaches 3 volts, and then it will jump the charging current up to approximately 900 milliamps. And as the battery voltage increases, it will basically go to its maximum of 1 amp charging current. When the battery voltage reaches its constant voltage, basically, let's say 4.2, just under 4.25 volts, the the TP4056 IC will start to limit the current that it's pushing into the battery, and you can see that with this curve over here. When the battery reaches this state, it will switch over to constant voltage charging. So similar to a linear regulator, for example. So instead of constant current, it goes to a constant voltage mode just after this point, and basically maintains the output of the IC to 4.25 volts. So around this output here on pin 5 will be steady at just under 4.25 volts. And the current that obviously is pushing into the battery will start to reduce until eventually it completely kills off the charging current. So the IC will maintain its constant voltage output and charging until it reaches a low current threshold. So you can see the low current threshold in this is 100 milliamps. So as soon as the output current is less than 100 milliamps, the IC will terminate charging. And at that point, it will basically indicate that the battery is full and switch states on the charging and the standby pins. This IC uses 2 pins for indication when it's either charging or discharging. So on this circuit, you can see I've put down 2 LEDs with 1K resistors, and it's connected to the charge and the standby pin. When the IC is charging a battery, it will basically connect this to low internally using a MOSFET, which if there is a internal circuit diagram, then I can show you that, but there isn't. But you can see the indicator light states over here. So you can buy these ICs pre-built, and they're quite popular for charging dead batteries. Sometimes they are delivered with these extra components. Sometimes they are just delivered by itself. These extra components, basically what they're doing is preventing the battery from being discharged too far, and they also prevent overcurrent as well. So just to show you the datasheet of this part, you can see the typical application, which is basically what I've copied. So the 2 MOSFETs are contained in FS8205A, which is a very commonly used part with this circuit. And you've got your battery connected to these 2 terminals. This component is basically a battery protection IC and is very commonly used with the TP4056 circuit. And what it does is it ensures safe charging and discharging of the battery by preventing overcharging, over discharging, and also providing overcurrent protection. And it does this by monitoring the voltage across the battery terminals. So you can see the battery terminals are connected to this IC from here and here. If this voltage goes above a certain threshold, which you can see on the data sheet over here, and the minimum value for the overvoltage protection is 4.25, and the maximum is 4.35. So obviously for safety, this value is more important. So it triggers the protection mechanisms inside the IC by controlling these 2 MOSFETs here, which essentially disconnects the battery from the application. The second function I spoke about was the over discharging. Again, it does it in a very similar way. So you've got the battery connected to the component, and if the voltage of the battery drops below the specified voltage, which in this case is 2.3 to 2.5, it will disconnect the battery again by activating its protection mechanisms. and disconnecting the battery using the MOSFETs in the circuit. The third function I spoke about for this IC was the overcurrent protection. Basically, how that is done is by monitoring the voltage drop across these two MOSFETs that are internal to FS8205A. So if you know the RDS on values of the two MOSFETs, you can work out by monitoring the voltage across it, the current that's flowing through it. As when the current is flowing through it, obviously with Ohm's law, you'll get voltage drop. And that's monitored through here internally with DW01. The positive side of the battery is passed straight to whatever you're connecting as your load. So the DW01 uses the negative side of the battery to do all its controls for over discharge, overcharge, and overcurrent protection. Obviously, if you have any questions on how this circuit works, please let me know in the comment section below. And what I want to do is add a microcontroller controlled switch on the input of this buck boost converter. And what I'm thinking to add is microcontroller controlled resistors, basically replacing R2. So I've been doing some calculations on what resistors I should use. So I'll just quickly show you that. So you can see here, I've put down 4 resistors in parallel. If I show you the circuit side by side with the resistors, so R1 is fixed at 1.8 megohms. The capability of this part is from 2.5 volts output to 8 volts output maximum. So what I want to do is control that output with a microcontroller. Now I'm thinking to do this by adding a BJT with a series resistor, and the BJT would be controlled by a microcontroller. I'm not sure, 100% sure if that's going to play havoc on the control algorithm and make the output unstable. So what I will do is add a bypass, using just the 200k resistor. So in case it doesn't work, I'll bypass all of the circuit using a 200k resistor. But these are the resistors that I am thinking to add in. So what I've got here is 4 resistors. Then I've got the 3 BJTs. So if all 3 BJTs are switched off, that basically means that these 3 resistors, so R2 corresponds with D2, R3 with D1, and R4 with D0. So if these are 0 or switched off, basically these resistors are disconnected from the circuit, and that means only R1 is connected. So the feedback resistor, the R2 value here, would be equal to 453k, and that would give me an output voltage of 2.5 volts. So that's using this calculation over here. Now if I switch in R4, so that's a 1.1 meg resistor, that will make the R2 value 320 kilo ohms, and that will give me an output of 3.3 volts. So you can see I'm basically switching in and out these resistors over here to get different output voltages. When all 3 resistors are switched in using the BJTs, I will have an R2 value of 120.5 kilo ohms, and that should give me an output voltage of 8 volts, so the maximum capability of this part. So hopefully this will make the circuit a little bit more interesting. I'm not 100% sure how it's going to work, but we'll test it and we'll see. As I said, we'll add a bypass for this just in case. The main thing I need from this board is 3v3 plus 5 and 12 volts. So as long as we have that, this is just an additional bit as a bit of a fun exercise to see if it will work. Thank you for watching today. Obviously, we just set up the TP4056 circuit, and in the next video, I will do the schematic layout and hopefully do the buck converter as well.